Hey guys, back in the Silverado here. Still not quite happy with our result that everything's fixed, but we didn't really do anything except for unplug a couple connectors and plug them back in. So you can see here, no codes present right now. I'm going to try to induce a couple codes. So we're going to try our bypass test again, just shorting the two, the white and the pink wires here. We'll try to short those out. Let's just see if we get a code. Take a couple of T-pins. Pretty sure I'm making contact here, and double check. You were shorting those two wires out, and what the heck? Nothing. So here, I shorted the known good, stage 1. And sure enough, we have a B0022 now, left front deployment loop 1, low resistance. Okay, cool. We pull a pin out, no codes. But why doesn't that work with stage 2? I mean, definitely making contact. Nothing. I don't know what else to do. We'll try unplugging it again. Maybe just jump the known good side and see what codes we have left. Alright guys, this is crazy. Past midnight, can't sleep until I solve this problem. That's how how this works sometimes. But check this out. I got a B0042 stage 2 low resistance. That is awesome. That means the module is not at fault. We have a wiring problem between the module and the airbag. Let me explain. So remember the experiment that we did shorting out stage 2 at the connector here, and first initially it fixed the problem, right? And then when we disconnected everything, took our leads off and left everything connected as it should be originally, there were no codes anymore. So that didn't make any sense. And right now I'm at the module again, and I'm shorting out stage 2 at the module. So I have my two T-pins. Yes, it's dark. Oh, come on. Right there. White and pink. Shorted out. Finally, we got our stage 2 to show low resistance on the scan tool, which means the module itself is doing what it should, and it can recognize if the circuit's shorted out. But if we short it out at the connector near the steering column, there's still enough resistance in the harness to simulate an airbag. So there's about 2.5 ohms of resistance between the module and the airbag. So let's ohm the wires now, the white and the pink, and see if we get a 2.5 ohm resistance somewhere. Hey, good morning guys. So I stayed up late last night messing with the airbags in the Silverado. I think I finally got a fix here, and I'll share that with you shortly. I just wanted to give out a shout out to Mark Hicks at Wells Electronics. I got this in the mail last night, fresh off the printing press. Thank you, Mark. If you don't know, Mark does a monthly webinar on the Wells website, and last week he featured a guest, Eric O from South Main Auto Repair. If you haven't checked out his channel, you can do that. But they discussed our Hyundai Tucson video with the twisted camshaft, and I think that was pretty cool. So I figured, I'd get a couple t-shirts out of that deal. But let's get back to the Silverado and see what the fix was. Alright. Alright, airbag. Continue, display codes, current codes, no codes present. So that's with everything plugged in, it's all good. Alright, let's unplug the connector, and what we expect to see, if everything's working correctly, is 2 codes, and they'll say open circuit for stage 1 and stage 2. So let's try that. Damn it. So we got the B0043 again. Okay. Let's try shorting out stage 1. So now it's showing stage 1 low resistance. Now short out stage 2. Alright, so now when we short out stage 2, we do get the B0042 low resistance code, and before we're actually getting no codes for that, and I think we have to go to the whiteboard of knowledge to explain that phenomenon. So let me plug this back in. No codes, okay, that's good. And now let's short out the 2 stages separately with the connector plugged in. Couple T-pins here. I'm shorting out stage 2. Okay, that's good. B0042, as we expected. Removing the T-pins, no codes. Shorting out stage 1, meaning the high to the low wire, just direct jumper across. There we go. Left front, yep, stage 1 low resistance. No codes present. So at this point I'm happy with how it's behaving, and I think we have to move on to our next issue here. Spend enough time on this, but we'll do a quick recap on the whiteboard. Hey guys, I thought it'd be a good idea to record the final segment on the Silverado airbag case study to just tie all the loose ends together, because that procedure, I mean, it went everywhere and things changed while we were diagnosing the problem, and you know, it started setting different codes and it fixed itself apparently. So like any proper scientist, we have to, you know, draw some conclusions and verify our findings, no matter how strange they are, or at least come up with a plausible theory of why we saw what we did. So let's get you focused in on the whiteboard of knowledge here, and we'll discuss for about 10 minutes or so and wrap this up. So here I have drawn up a very simple schematic of a circuit, one of the stage 1 or stage 2 of the airbag deployment loop. And this is our sensing diagnostic module, basically the airbag controller. And here, marked as a resistor, is the actual the actuator for the airbag. Now let's define a few things here, because what the module is looking for is a specific resistance that the airbag actuator has, and it monitors the two legs of the circuit and looks for that resistance, and then sets codes if we're not in that specified range. So RA here I've labeled as the resistance of the actuator. Then RP I'm calling any parasitic resistance that we might have in the circuit, and that'll come from the wires or the connectors. So we have 3 connectors going to our airbag. So one is right at the module, another one is behind the kick panel at C221, the one that we were back probing under the dash panel is C275, and obviously the actuator connects right at the steering wheel. And there's also, I didn't draw here, the coil. You know, so when you turn your steering wheel, the wires don't get torn off, so that's another potential for parasitic resistance. And then if we add those two together, we get the total circuit resistance RT. So that's simply RA plus RP. Now let's see what the diagnostic module is looking for, since it's measuring resistance of this circuit, and see what good values are and what's too high and what's too low. And for that we'll go to all data. Okay, so here we have our flowchart and description for the airbag actuator codes. So you see it's one article on the 22, 24, 26, 42, 43, and 44 trouble codes. And here just defines all of them and also puts them in this handy chart here. So we have short to ground, high resistance, open, short to voltage, and signal performance. Alright, so the initial code that we saw was B0044. So that's for stage 2. So that would mean an open circuit, or the threshold resistance for setting this code says driver module stage 1 or stage 2 deployment loop resistance is more than 4.8 ohms. So that's a key number right there. So if the resistance of that whole circuit, RP plus RA, is greater than 4.8 ohms, we're going to get this code. So it doesn't need to be an open circuit like infinity, it just needs to be higher than 4.8. Now what about the other scenario? What if we have a short circuit? What is it looking for? So the 22 and 42 codes. So if the module deployment loop resistance is less than 1.3 ohms for 500 milliseconds. So that's our cutoff on the other side. So if this total loop resistance is less than 1.3 ohms, we're going to get the 22 or the 42 trouble code. So let me write that down real quick. So what we're looking for, the range of our total needs to be between these two values, and on the high end we have 4.8 ohms, and on the low side we have 1.3 ohms. And if the resistance is too low, we'll get the B0042. This is for stage 2. So B0042 over here. And this will be, our OK range. And on this side we'll have our initial code of B0044. Alright. So now, knowing that piece of information, let's go back through our case study and explain what we found and what changed throughout the process and where the problem actually was. Alright, so initially, when we first started working on the truck, we noted that the code B0044 was a hard fault, and that means, according to our information, that our total circuit resistance was more than 4.8 ohms. Right? Now, when we measured, disconnected this connector and measured the resistance of just the airbag actuator, on both stages we got a consistent, about 2.5 ohms, so let's call it 2.7. So I'm going to take that as a constant value there. So now we can actually figure out, using this equation, what our parasitic resistance would be in that case. So we just take our total resistance, which is greater than 4.8, subtract 2.7, and we conclude that our parasitic resistance in stage 2 was greater than 2.1 ohms. Okay, so that's the scenario for our initial experiment. So the second experiment that we did was actually shorting out the two sides of the stage. So you can picture that as taking the actuator out of the picture and just shorting out these two pins here on the connector under the dash. So that resulted in a no codes message on the scan tool. So the system was happy, even though we shorted this, these two pins out. So according to our specification, that would mean that our parasitic resistance is actually, correct as if there was an airbag in here. So it's between 1.3 and 4.8 ohms, but we know it's higher than 2.1 ohms since we had a hard fault to begin with. So we can narrow it down that our parasitic resistance is somewhere between 2.1 and 4.8 ohms from the second experiment. Okay, so the third experiment that we did, inadvertently, after disturbing the connector at the diagnostic module the first time, I was back probing it, actually took it off, looked at it, put it back in, our results changed. So when I plugged everything back in, the scan tool showed no codes, even though initially we had the 44. So what does that mean for our parasitic resistance? Well, now, since our total resistance is within this range, that means our parasitic resistance would have to be less than 2.1 ohms, right? Since now it's the total resistance is less than 4.8 and our airbag resistance is 2.7, subtract the two, you get 2.1 ohms remaining as your threshold for the parasitic resistance. Now, also, once we saw that, oh, we have no more codes, let's try to short out the 2 wires again. It stayed at no codes. So, in that case, our parasitic resistance is still greater than 1.3 ohms, since we didn't drop below this threshold. And I was looking for this 42 code. That's what I wanted to see at this connector when I shorted the low and the high sides out. I still didn't see that. That's why I felt uncomfortable leaving the system the way it was, because even if there was a short, the system would still think that there's an airbag, and that's not the right way to leave it. So after this initial disturbing of the connector, our parasitic resistance actually dropped from, before it was in this range, between 2.1 and 4.8. Now we know it's between 1.3 and 2.1. And obviously, ideally, it would be 0, but our threshold, so for a normal system, when we short this out, we want to see this B0042 code. So we want our RP, parasitic resistance, so it's in this range now, we want to get it to below 1.3 ohms. So in that case, when we do short the wires out, we will get the right code. So we're starting out with RP between 2.1 and 4.8, and we're shooting for, we want RP less than 1.3 ohms for a normal system. So you can see how sensitive this whole system is. I mean, even if you connect your voltmeter leads together, just together, you'll get non-zero resistance. You have resistance in your wires, and not to mention all these connectors. So a little bit of either pin fitment or corrosion on there, or anything that gets the total resistance, parasitic resistance, above 1.3 ohms will mess up the system. So that's why this is so finicky. We saw the signals there coming from the module, the wiring looked good, the integrity looked fine, but the system still wasn't happy because our parasitic resistance is just a little bit higher than that threshold. So finally, after messing with this connector some more, the residual, or the parasitic resistance, did drop below 1.3 ohms, and the system is now happy, and we can set the 42 code by shorting out the 2 wires of the connector out here. So it was kind of a, I'm not really happy with that fix. What's to say that this connector doesn't get loose again? The pins look fine, and there's no real way to widen them or get them to fit any better. So sometimes that's the way it goes. There's no real clear problem until you start playing around with a couple of these variables. In terms of TSBs in this subject, we can go to our BBB Industries. And there are a couple of TSBs for these Chevy trucks on what could happen to the sensing diagnostic module. It lives under the driver's seat, so there have been cases of extreme corrosion for this code. There's one on the actual connectors. There's a whole host of TSBs. The intermittent restraints. That one talks about just the connector under the dash or the kick panel not seating all the way, but that wasn't the case here. So long story short, there is no TSB describing this condition of just poor connection at the diagnostic module, at those pins. And you can see that that is such a low threshold. I mean, that's nothing at all. You wouldn't think that would be considered a bad wire or a bad connection, but in this case it is. And off camera, I actually, to eliminate any other variables, what I did was integrity test of just the wire separately, and you would think the only way to do that is to ohm it here to here, and I did. I got about 0.4 ohms on the pink and the white wire, or I think this is pink and this is white. But always put your units. But then, even if there's like one strand connecting them, there's a partial break, you still get a resistance number, but you need to test it under load. And what's a way to load up a wire where the circuit itself is a low current circuit, especially with an airbag? You don't want to put current in the actuator. So what I did was I hook up a test light. So disconnect the two connectors, hook up a test light to battery positive. Here's your light. Hook it up to this end of the wire. Run your current through, and then ground this side. Alright, so you're going to have about 200 milliamps of current running through. And then just put your voltmeter across the wire here and here, and watch your voltage. And in this case, I had about 0.20 volts, so 200 millivolts. You would think that's a substantial current drop, but for 200 milliamps running through skinny wire, that's okay. And I did measure both of them and also the other stage, and they're identical. Well, one of the wires was a little higher, but a few tens of millivolts higher voltage drop in this case is not substantial. So the only explanation for this problem is bad contacts right at the module. And there's no real good way to verify that except for play around with it, look at your codes, play around with it some more. And I don't really like that. That's the only way to really test it, see if the module is happy. I mean, how else are you going to test the resistances of connector at the module? That's not really feasible. So hope this was useful to you. I mean, I thought it would be a short video, how to do a circuit check on a wire, but it kind of turned into something a little more interesting, which I guess makes for a better video. But anyways, I want to say thanks for watching, and look forward to more videos from Pine Hollow Auto Diagnostics. I guess this was part 2. I'll probably do a separate video on the evap system. So enjoy the video, and hope to see you guys later. Alright, bye.